Log on, tune in, find out. Another good idea from Cambridge.
This is an informal seminar or lecture series, so I shouldn't really give an introduction, but I would like to give an introduction nonetheless. So it's a pleasure to welcome Professor Hans Duistermaat to the program. And he's officially appointed as the Rothschild Professor in the program, so appointed by the University of Cambridge. In that context, he will also give a more wider published or advertised lecture on the 18th of May, where he will give a kind of more proper introduction to his work.
Yeah, and that lecture will be for a much wider audience.
Yes.
So here I will dare to be more special.
Yes.
More specific.
So we're grateful that Hans agreed to give us a series of lectures. Maybe, well, we have to see how it will develop over the coming weeks, but it might be 1 or 2 or 3 lectures on the subject of what actually is the subject of a book that is in the progress of finalization on QRT and elliptic surfaces.
Right.
And so I'll give you the floor.
Thank you. So the title is QRT maps. And elliptic surfaces. And I would like to use the opportunity of these informal lectures also to pose some questions which are still open. For more than 3 years I've been completely obsessed by the subject, and it resulted in this book which Frank mentioned, which since half a year I've been saying it's finished, but then the next day I find something which really can be improved and therefore should be improved. And but now before I came here to Cambridge, I decided that now it is really finished, so that I'm free to think of new other things. But there are, despite the fact that I've tried to understand as much as I could about QRT maps and elliptic surfaces, I have still some open questions also, and so I would like to take this opportunity to mention them. But in order to pose them, they are a bit technical. I first have to tell a number of things which I do understand. So let me begin by just repeating the definition of QRT maps. It starts by considering a polynomial in 2 variables, which is biquadratic. And that means that if you fix y arbitrary, then as a function of x, it has degree 2. And if you fix x, then as a function of y, it has degree 2. And this has the following consequence. If you draw the curve p equal to 0, which then of course is called a biquadratic curve, then fixing y means that you are on a horizontal axis at the level y, and then the fact that as a function of x the polynomial has degree 2 means that it has 2 zeros, and that means that there are 2 points of intersection. And then once you have this situation, then you have the switch of these two, the interchange of these 2 points of intersection. And I call this the horizontal switch. For every value of y, you have this horizontal switch, and so this is an involution of the curve. It's a self map of the curve, and if you apply it twice, you get the identity. So this is, you could also call it the horizontal involution. You know, but I prefer the name horizontal switch because it just switches the 2 intersection points on a horizontal axis. Now, as a dynamical...
Two out of x and y being real and the long have
No.
real roots?
No, I will comment on that right away. I welcome very much when people ask questions because it helps me in filling in details. The theory is certainly interesting in the real domain, but the theory becomes much more uniform, much nicer, if you work over the complex numbers, because then you always have zeros of polynomials. It's not quite true, because if you have a quadratic polynomial in the familiar ABC form a times x squared plus b times x plus c, then when a is equal to 0, it looks like a linear polynomial. But what actually has happened, if a goes to 0, then one of the zeros runs off to infinity. So not only I want to work over the complex numbers, but I also want to work projectively. So everything is compactified with suitable points at infinity. So actually the biquadratic curve for me is living in the projective line for the x variable, Cartesian product with the projective line for the y variable. And the complex projective line in order to have an algebraically closed field. But you can always, in the case that the coefficients of the polynomial are all real, you can look for the real locus. And so that will be the point of view actually, that first develop the theory over the complex numbers, and then if you are interested in real questions, then just look at what happens on the sub-variety, which is the real locus. And then it turns out that, for instance, classifications, they become actually more complicated if you include this real structure. To start with, I take the complex projective point of view. And then you always have these base points, and then this is always defined. Not quite true, actually. This is one of the problems which immediately arises. You can have a biquadratic polynomial which factorizes in a linear one, for instance, the y-coordinate times something. And in that case, you have a horizontal axis being one irreducible component of your biquadratic polynomial. And if you are on that horizontal axis, then you cannot define the horizontal switch. There's no way to know what the image points would be. So in such exceptional cases, that's of course a singular curve. That would be a curve like this, but this being one of the reducible components. Then on this part, the switch is well defined, but not on this horizontal axis, which then would be a component of the curve. So in such exceptional cases, the map is actually not defined. But in most cases, it is defined. Only except such things. So we have this horizontal switch, and another observation, which is quite obvious, is that this horizontal switch is a rational map, because the sum of the two zeros, if you think of the ABC formula, is equal to minus b over a. You remember this thing with minus b over 2a plus or minus square root of a discriminant, that kind of stuff. But the plus or minus square root of the discriminant drop out if you take the sum of the two roots. And so you get this formula. And since b and a are both polynomials, this becomes a rational formula for x for one root in terms of the other root. Yeah?
Make sure that the horizontal switch
Yeah.
is a mapping from the curve to itself.
From the curve to itself. It's only defined on the curve. Yeah. So that's the horizontal switch. And as a dynamical system, this mapping is not very interesting, because if you iterate it twice, you get the identity, and that's it. Then it stops doing something. So now you combine this with the vertical switch, which we also have for the same reason. Interchanging the role of x and y, you also have a vertical switch. And so by definition, the QRT map of the curve p equal to 0 is defined as do first the horizontal switch and then compose it with the vertical switch. You can also do it the other way around and then you get the inverse of the map. But this is the QRT map of the curve. And this is already quite interesting transformation of the curve to itself. If you iterate that one, it runs around on the curve in an interesting way. And usually you have that it is not periodic, but once in a while you can have a biquadratic curve on which the thing is periodic. So there's all kinds of interesting questions about that. I will come in a minute to describing how it acts on the curve. But this is by definition the QRT map on the biquadratic curve. But this is not what Crispo, Roberts and Thomson did. They defined a map from the plane to itself, from the whole plane to itself, not from just a curve to itself. So in order to explain that, I take, instead of one biquadratic polynomial, I take two linearly independent biquadratic polynomials, so P0 and P1, linearly independent biquadratic polynomials. And then I make an arbitrary linear combination of that, P0 xy plus z1 P1 xy. So that will now be my P of x and y, but it depends on z, on the choice of z. And now I play this game and I take a non-zero linear combination, because otherwise the curve p equal to 0 would be the whole plane. I don't want to do that, of course. So I take this and look at the corresponding biquadratic curve and the QRT map on this biquadratic curve. So now the observation is that this biquadratic curve forms a family depending on z. But it is not a two-parameter family, it is a one-parameter family of curves, for the simple reason that if you multiply z0 and z1 with the same constant, then you get the same curve. Then you get the same zero set, it doesn't change. So actually, the family of curves is parametrized by the set of all one-dimensional linear subspaces of the z0, z1 space, if you allow me this kind of formulation. So it's, this defines a family of curves parametrized by a P1, where the linear subspace spanned by z0 and z1 determines which curve you have. And that's a point in the projective line. So it is parametrized by a projective line, and now it depends on your intuition. For me, projective line is all one-dimensional linear subspaces, and for me this turns around. But projective line, some people also think of it as really a straight line, and that is why the name pencil came in, because a pencil is straight. So the word pencil comes from this projective line. But in Dutch, the name is fan. This kind of, yeah, and I prefer that name actually. Yeah.
Hans, do you mind if I make a comment? People often talk about what's called the Macmillan map.
Yeah.
And if your formula x plus plus x minus equals minus b on a, that is actually the Macmillan map on that curve. And so this idea of then taking the Macmillan map over a family of curves is a little bit this perspective
Yeah.
that Yatra and I took in 2001. So the QRT is a one-parameter family of Macmillan maps assembled in a particular way.
Yeah. Okay.
Yeah, so the map on the curve is actually what some people might call the Macmillan map.
Yeah. I think the Macmillan case is that one of these two polynomials, for instance P1, in affine coordinates is just a constant 1.
That's
But
true.
if you write it in homogeneous coordinates, it's not a, it's again a biquadratic polynomial, and its zero set is very weird. Actually, it is a horizontal axis at infinity with multiplicity 2. That's why I write it as a double line. Union with vertical axis also at infinity with multiplicity 2. And that is what corresponds to the constant in the Macmillan family. And that is a very funny biquadratic curve, a very degenerate one.
It's just that on any curve, the QRT map, which has these quartic polynomials,
Yeah.
acts like a Macmillan map, and
Yeah.
it's really that x plus plus
Yeah,
x
yeah,
map.
yeah, right. So now the strategy is as follows. There are two different kinds of points in P1 cross P1 in the plane. And you have to distinguish two cases. Let's say case 1 is that P0 at the point xy is equal to 0 and P1 at the point xy is equal to 0. If this happens, then for every value of z, you have that P sub z x comma y is equal to 0. And that means that all curves in the family pass through such point. So if this happens, then x comma y is called a base point. Base point of the pencil. You can do this in algebraic geometry much more generally with any two-dimensional space of polynomials and talk about the base points of the pencil of curves defined by those two polynomials. Yeah, and then so any such pencil has base points usually. And the base points, you can count how many you have because it is the intersection of two of the curves. This is one of the curves, that's another one of the curves, and you just count the number of intersections. And the nice thing about intersection numbers, if they are counted correctly with multiplicities, is that they are homology invariants. In particular, they are homotopy invariants, and so it doesn't matter which curves in the family you take, which two curves in the family you take, the intersection numbers are always the same. And it happens that the intersection number of two biquadratic curves is equal to 8. So you have 8 base points when counted with multiplicity. Everything working over the complex numbers and projectively. Otherwise, such statements are not true. If you look at the real locus, then you can have much fewer base points. If you cut out infinity, then you can have much fewer base points. Actually, many of the explicit examples, a lot of the base points are lying at infinity, and if people only look in affine coordinates, then they don't see them. But they are really there. Let me show you a picture of, pictures usually are real, because it's a bit difficult in a complex surface. Complex two-dimensional is a real four-dimensional. And a complex curve is real two-dimensional. So it's a bit difficult to visualize real two-dimensional manifolds in a real four-dimensional space, and even harder to visualize a family of them parametrized again by a complex number, which is real two-dimensional. That's quite hard to make a good picture of that. So I only make real pictures. And this is an example of a pencil called the Discrete Sine-Gordon pencil, but the real version, where you can have 8 real base points. If you count them, you see the base points are the points where all the curves go through one and the same point. And there are 8 of them in this picture. Now you have the other case, is that this is not true, so that P0 x comma y not equal to 0, or P1 x comma y not equal to 0, or both. And if that happens, then the set of z0, z1s for which this is equal to 0, now you fix x comma y. And now you look at the z0s and 1s for which this is equal to 0, because z0 and z1 appear linearly, this is a one-dimensional linear subspace. And therefore it is a unique point in P1. And that means that through every other point there is a unique biquadratic curve going through it, a unique member of the pencil going through it. This is another characteristic property of pencils of curves in general. I mean, it need not be biquadratic, you have the same phenomenon for any pencil. So then through x comma y passes exactly one member of the pencil. And now comes the recipe of the QRT map in the plane. You take an xy, not a base point, then you assign to it the biquadratic curve through x comma y, and then to that you assign the image point of x comma y for that biquadratic curve. The QRT image of x comma y for that biquadratic curve passing through that point. That is the recipe of the QRT map. And since everything is rational, this defines a rational map from the plane to itself. But it is not a map. I mean, this was the first thing when Thea Tuonkota in December 2005 showed me that kind of picture. The first thing which I observed, that this so-called map is not a map. It's not defined at the base point. A map should be defined everywhere, and this is not. So this is what is called a birational transformation of P1 cross P1 to itself. But birational transformations have points of indeterminacy, where they are not defined. And actually, this map is not defined in a very bad way at the base points. Because if you are near such a base point, you do have the unique curve going through it, but arbitrarily near that base point you can take any of the curves, and then the image points will be very different. You will get a whole curve of image points. So a base point by this map will be blown up to a whole curve, and actually to a P1, because you have this whole P1 of curves going through the base point. That is what happens at the base points. So maybe it's a good moment to make a step back to the biquadratic, to the QRT map on the curve, and to analyze what the QRT map on the curve is doing. So let me first make a statement that if the biquadratic curve, and this is if and only if, the biquadratic curve is smooth, then it is an elliptic curve which one characterization of elliptic curve is that it is isomorphic as a complex analytic curve, complex analytic object. to a complex plane modulo a period lattice. Period lattice means a subgroup, discrete, co-compact, so that this looks like a real two-dimensional torus from the real point of view. It's a real two-dimensional torus. And then this here has the structure of a group. You have translations on them. And so the next statement is that the QRT map on it is a translation in this picture on this torus. And that makes it, from the dynamic point of view, very well understood. Yeah, just translations on the torus. So let me give my there are several proofs for this, but my favorite one is via Hamiltonian systems, because I come actually from differential equations. I'm actually an analyst, and I had to learn a lot of algebraic geometry in order to understand everything about QRT maps. But I do not betray my upbringing. So for me, my favorite way of proving this is as follows. If you have a function, two variables in this case, so now I regard this function in affine coordinates. So now x and y are just complex numbers. Then I look at the Hamiltonian system defined by the function p. And then what can be verified very easily is that if you have a solution curve of this, then the ddt of p x comma t, if you substitute that in the function p, then this ddt is equal to 0. And that means that p is constant on any solution curve of the Hamiltonian system defined by the function p. And that means in particular that p equal to 0 is invariant under the flow of this Hamiltonian system. More geometrically, this means the following, that this vector field which you have here on the right hand side, this vector field is tangent everywhere to the curve, p equal to 0. Yeah? So I have this picture that in its curve I have this Hamiltonian vector field. And now comes the following simple observation, that x comma y is a smooth point of the curve if and only if the gradient of p at that point is non-zero. But that means that the vector field is non-zero. So at smooth points, this vector field is non-zero. But this was in affine coordinates. And I was doing these biquadratic curves in P1 cross P1, so I also have to look at this Hamiltonian system in the new affine coordinates around points at infinity. Now this is very easy exercise. The new coordinates around infinity is that you replace x by 1 over x. And if you take y at infinity, you replace y by 1 over y. And you just look at the Hamiltonian system in the new coordinates. And lo and behold, in the new coordinates, and this is really due to the fact that the polynomial is biquadratic, here you use it very much, very strongly, that at infinity the vector field extends smoothly to the points at infinity. And if at the point at infinity the curve is smooth, then again the vector field is non-zero. Because in the new coordinates, new affine coordinates, it's again Hamiltonian actually for the correct function p in the new coordinates. So this extends. These statements here extend to the points at infinity. But now we look at this system, everything is complex numbers, including the time. You can look at differential equations with complex t. And so what I now do is I look at this flow on the curve, parameterized by this complex time, and I take this time parameter in order to parameterize the curve. That's a very good idea because the vector field is non-zero. So you really move at every point. So now the argument is that the flow is a group action of C. Flow is a group action of C on the curve, the C action on the curve. And it is locally transitive because the vector field is non-zero. And that means that every orbit of this group action, every orbit is open. And since the curve falls apart into disjoint orbits, and since the curve is connected, that you have to verify separately, but that's very easy, there is only one orbit. And that means that the action is transitive, and that means that this time parameter induces an isomorphism from this to the curve, where p, by definition, is the period lattice. Those are those times for which, if you start at a given point, you return to after that time to the same point. That, of course, you have to model out in order to get a bijective map. Otherwise, the map is just surjective, and that's not what you want.
So can this be viewed as a complex version of the Arnold argument for proving Liouville-Arnold?
Yeah, correct. Even part of the argument is that since this curve is compact, if you work in P1 cross P1 is compact, so P1 cross P1 is also compact. So this curve is also compact. Since this is compact, this lattice must be two-dimensional, because C modulo a one-dimensional rank 1 subgroup is not compact. So
well, you can also say that this is algebraic, so that the bundle is triggered, so there is only one vector field essentially up to constants.
Yeah, that's another thing which immediately follows. And you can, for instance, look at holomorphic one forms on this curve. If you pair the holomorphic one form with the vector field, you get a holomorphic function. But on a compact connected curve, a holomorphic function is constant. And since if I assume that my holomorphic one form is not everywhere zero, then this constant is non-zero, but then the holomorphic one form cannot have any zeros. And every other holomorphic one form is of the same form, and so it's a constant multiple of this first one which I started out with. So the space of holomorphic one forms is one-dimensional, and every non-zero one has no zeros whatsoever. And that is what another characterization of elliptic curves. So this way you see that it is an elliptic curve, but I like this picture because it makes possible for me in a very simple way to talk about translations on it. This is automatically the case. So why is it a translation? I didn't tell you that. That can be verified also very easily. The map is a composition of the horizontal switch and the vertical switch. And now what you verify, and this is a verification of maybe 2 minutes, that the horizontal switch maps the Hamiltonian vector field on the curve, you have to restrict yourself to the curve, to its opposite. But that means that if you compose two such inversions, where the where the vector field is switched to its opposite. If you compose two of them, then you get a map which preserves the vector field. But if it preserves the vector field, then it preserves the motion in t, in the time parameter, and so it is a translation. Yes. That's the only way what can happen. If the vector field is preserved, then any map which preserves the vector field must be a translation in the time parameter of the solutions. Yeah, so this is my preferred way of looking at it, but I easily, I mean there are many other ways, and they are also beautiful. But it ties in with some other things which I want to talk about. But oh, there's still some time. Yeah. So so far for what the map is doing on an individual curve. Now you have this pencil of biquadratic curves, and for each of them you have this translation on the biquadratic curve. So you have now a one parameter family of those things. And yeah. So one of the interesting questions for me is, for instance, you could have a biquadratic curve on which the map is periodic. Mean that after you iterate the map a number of times, you can come back to the same point, and that means that the translation vector which you have is equal to 0 after you iterated a number of times. So one of the questions I was interested is, for which parameter values z, which tells you on which curve you are, do you have a k-periodic map on that curve? And it turns out that this set of z values is a very nice finite subset of P1. And, I will show you some pictures later of that. But looking at this one parameter family makes it richer. There's more to say about that. Now I want to go to elliptic surfaces. So I think I have repeated the definition of QRT map in sufficient detail. Now I want to go to the elliptic surfaces. And that is the following point, that these curves, they don't form a fibration of the plane, because they are not disjoint. You have these base points where all the curves of the family go through the same point. But you can remedy this by blowing up the base points. And blowing up is the construction that you replace the point by the one-dimensional projective line consisting of all one-dimensional linear subspaces of the tangent space of the surface at the given point. That is blowing up a surface at a point. And the interesting thing is that in this construction produces a smooth surface. You wouldn't think so, because this looks like a very drastic operation. We place a point by a whole P1, but the result is smooth. And that the result is smooth, I can illustrate with a real version of blowing up, which gives a very nice picture. I hope that I can find that picture, because it's a bit of a mess here. Yeah, here it is. So the pictures are always that the surface which you blow up, you always do that downstairs, that surface, and the new surface is upstairs. And you have a map from upstairs to downstairs. There is no map the other way. And what you do is you just stack all one-dimensional linear subspaces which go through the origin. You stack them, but make them disjoint. So you add an additional parameter in the vertical direction to make them disjoint. And so what you then get is this surface which is like a spiral staircase with a central axis in the middle, where the surface becomes very steep. But as you see, the surface is beautifully smooth. And if you look at over you also see that this point has been replaced by this vertical line. And if you look at the complement of the point, then it is a bijection between what happens upstairs and what happens downstairs. So this projection to this downward projection is an isomorphism from the complement of this vertical P1 to the complement of the origin downstairs. That's one of the properties of blowing up, that in the complement of the point, or the pre-image of the point, you have an isomorphism. But it is of course not an isomorphism, because the map contracts this whole vertical line. In order to understand this real picture, you have to keep in mind that the one-dimensional linear subspace I started out with, after turning around, after some time, it comes back to the same one-dimensional subspace. So the bottom line has to be identified with the top line. And if you do that, and you look at the surface, you recognize the Möbius strip. So the real version of blowing up produces a Möbius strip, which topologically is non-trivial. And so already in the real picture, you see that something topologically highly non-trivial happens. In the complex situation, this is reflected by the fact that you have this exceptional P1 lying in the surface above. This is the surface above, and then you have this projection, downward projection where this is contracted to the point, that the intersection number of E with itself is equal to -1. The self-intersection number is equal to -1. And since the intersection number is a homology invariant, this shows that this exceptional curve, which is produced by the blowing up procedure, is homologically non-trivial. It cannot be contracted to a point. And therefore, you are making the topology of the surface more complicated by doing a blowing up. You add one cycle to the two-dimensional homology group. So the H sub 2 of the surface with values of C, with values in Z, increases in rank by 1. And actually, the homology class of this thing is independent of what you had before. So you're really, the new homology group is just the old one plus Z, direct sum with Z. So that is the way how the homology group changes, in a very controlled, simple way. But it is more complicated. Yeah. The algebraic way of doing the blow-up is very simple. You replace points by the central point by the lines through the origin, and that corresponds to that you make the following substitution of variables. You leave, for instance, x as it is, but you replace, but for y, you make the substitution of variable y is equal to x times eta, where eta is a new parameter. And you immediately recognize that eta is equal to the ratio between y and x, so it tells you which one-dimensional subspace of the two-dimensional plane you have. So this y is the coordinate along the vertical axis, if you understand what I mean. And if you, for instance, have any polynomial in x and y, and which vanishes at the origin, and you make this substitution, then you see that x becomes a factor in this polynomial in the new variables, x and eta. And if you ignore that factor for a moment, then the polynomial simplifies. And this is why singularities of curves become simpler when you do blow-up. And I like to write down this formula for a moment because I hope that it convinces you that blowing up is nothing mysterious at all, and that it is very easy to make computations with it. There's
nothing much in some sense.
And this has been discovered at least by the Italian geometers in the 19th century. End of the 19th century, this was very common tool in order to simplify situations. But they already also were realized that the surfaces which you get by doing the blow-up are more complicated than the surfaces which you start out with. But the singularities of the objects in the surface become simpler. So it's really a computational tool in order to understand things better. The whole process of blowing up has been rediscovered by Heinz Hopf, and he called it the sigma process for the following reason, that a complex projective line is topologically the same as a real two-dimensional sphere. So the word sigma, the letter sigma refers to the sphere. I think sphere is a Greek word, isn't it? Starting with a sigma. So I've not had Greek or Latin, so that's why he calls it sigma process. And for Hopf, who was a topologist, the interest of the sigma process was that in this way, by applying it, you could make new manifolds which are more complicated topologically. Yeah? A way of creating new things. Okay, so what you do is you blow up the base points, and for instance, if you have a simple base point, let me put back the first picture which I had, because there all the 8 base points are simple. If you have simple base points, then at the base point, each member of the curve of the pencil, each member of the pencil is smooth at that point. And also, all the tangent lines are distinct. And the tangent lines form the full P1 of all one-dimensional linear subspaces of the tangent space at the point. Yeah? And that means that if you do the blow-up there, then you separate all these curves automatically. They become automatically disjoint. And so if you blow up if all the base points are simple and you just do blow up at those base points, then you get a nice smooth surface on which now all the curves have become disjoint from each other. If there's a multiple base point, then the situation is a bit more complicated. Let me see whether I can find a picture of a multiple base point. Okay, this will do. It's not the best picture, but this is a picture of a multiple base point. And what happens here is that there is exactly one member of the pencil which is not smooth at that point, which has a singularity at that point. And that is here depicted by the cross, the union of the horizontal and the vertical axis, this black cross. That is one member of the family here, which happens to have happens to have its singular point, which is a normal crossing, right at the base point. But the claim is that there is exactly one such singular one, and all the others are smooth at the base point, but they have a tangency of order 2 with each other. So they all have the same tangent direction. If you now do the blow up, then you get the following picture.
May I ask a question?
Yeah?
What is the definition of simpleness for base point?
Simply you take two members of the pencil and you look at their order of intersection at the given point. Their intersection. You have also a local intersection number. At every point where they do intersect, you can talk about how much is the contribution of that point to the total intersection number of the two curves. And that's the multiplicity of the... And it doesn't depend on the choice of the two curves. So I suppose I start out now with this picture which I have there, and then I do the blowout. So I again have this exceptional curve after the blowout. But then all these things have the same tangent, so that means that there is a unique point upstairs there, which corresponds with this tangent direction. At that point, you get that now the curves are smooth, but also their tangents now become distinct. And that means that if you now blow up again at this point, once more, then the curves become nicely disjoint again. And I like to give this example because it shows very well how the count is always correct. If you have a double base point, you just blow up 2 times over that base point. First you blow up the base point, then upstairs you get a new base point, you blow up again. And after having done that, you have separated the curves over that point. And this count is always correct, even if you have an 8-fold base point, which can happen, because there are in total 8, and it could happen that they are all at the same point, that you have one 8-fold base point. You have to blow up 8 times, and after the 8th time, you have that the curves are separated, but not before. Before they keep on not being separated. But that's quite funny to see that happen in every example. So what this does for you is, and then I stop and we have a little break, okay? I'm a bit over time, but so what this does for you is you get a smooth surface S, because every blow up of a surface at a point produces again a smooth surface. It is compact, because the thing you start out with is compact, and you only and locally this map is proper, meaning pre-image of compact subsets are compact, and so this new surface is smooth and compact again, and connected at every word which you can imagine, every nice property it inherits from the surface below, but it is more topologically more complicated. And since I blow up 8 times, actually I know the H2 of this surface above. I will write it in a minute, but let me first say what we have here. You have this projection downstairs. Every blow up corresponds to a projection from the higher surface down. So you get a sequence of such projections, and you just compose all the projections. You get a projection from here to P1 cross P1. And if you here take the complement of the base points, which means above the complement of the pre-images of the base points, and these pre-images are curves, then over the complement, this is an isomorphism. But it contracts all these curves to these base points. That's what this map is doing. And then downstairs you have this pencil of curves with base points, and upstairs we have now a fibration by curves. And another way of phrasing this is that you have a map fibration by curves, that you have a map, let me call it kappa. In the book it's called kappa. I have a reason for that, but I don't want to. A map to P1. In such a way that if you take the pre-image of a point of kappa, it is the curve corresponding to the curve down here. The curve in S, which is mapped by pi to the biquadratic curve, this member of the pencil down here. But since now these curves down here become the fibers of a map, it is obvious that if you have 2 distinct points here, then the pre-images are disjoint from each other. Yeah? So this is another way. So what is this kappa? It is nothing else as you take P0 divided by P1 of x comma y and view it as a map from P1 cross P1 to the projective line. This is a complex number, but it can happen, for instance, when P0 is non-zero and P1 is equal to 0 at such a point, then you get infinity. So that's the point at infinity in the projective line. It can also happen. But this function is not defined, of course, as points where both numerator and denominator are equal to 0. And those are precisely the base points. At those points, the map is P0 divided by P1, this rational function, is simply not defined. It's completely undetermined. But upstairs here, it is. Because I separated all these things, you see that it really amounts to, so this kappa is equal to P. So I should make this the diagram this way. You have kappa here, and here you have P. What did I do? P0 divided by P1. This map is not everywhere defined, but where this composition is equal to that map. That is one. And second, in the domain where this has an inverse, you can define this one as being which one? This one as being take the inverse of this and then do kappa. So kappa is really, you can think of it as just being this rational function, but then on the surface. But of course the point of this is that now this rational function, which has points of indeterminacy down here on P1 cross P1, now is a globally defined map from the surface to P1. Yeah? I think this is high time now to have a break. Shall we take a quarter of an hour? Yeah? So after the break, I would like to mention some consequences which one can draw from the fact that now everything is nicely globally defined as maps. And you can do then some things which you cannot do with these funny birational transformations, which are not really maps, and therefore you cannot apply certain things which we are used to applying to maps. Okay. One application of this picture. So one application was already that the rational function P0 divided by P1 now becomes a globally defined map from the surface to P1, and the curves turn into being the fibers of this map to P1. And since the generic, I always assume that the pencil of biquadratic curve has at least one smooth member. If that does not happen, then you get something completely different. Then every curve is singular. You desingularize the curve, you get P1s only. And then what you then get is actually what is called a ruled surface, which is a completely different animal and much simpler actually. But that's not the topic here. So I assume that at least one of the biquadratic curves is smooth, and then I will discuss that also in more detail. Then you have 12 singular curves if you count with multiplicities. The number of singular curves is equal to 12 when counted correctly. This means that once in a while you can have less singular curves, but then some of the singular curves are more singular than others. It's like in this book of, who was it, that some are more equal than others. But I want to give an application which I think is quite interesting. So let me call tau, let me call that the QRT map with an S hanging over it, viewed as a map from S to itself. Now a priori this is not a map, because down here it was not a map. So you have to work in the complement of the base points, but on the complement of the base points, pi is an isomorphism. And so there I can use pi in order to conjugate the QRT map in P1 cross P1 with a map going from the complement of the preimage of the base points to the to something in S. So there I have a map from S to S. Now it is a theorem that if you have a map from such an elliptic surface to itself, which is not everywhere defined, but the set where it is not defined is of lower dimension, yeah, so it's generically defined in an open, Zariski open subset, there it is defined, and if it preserves the fibers wherever it is defined, leaves the fiber invariant, and that is certainly true for the QRT map, because this was by definition the translation on these elliptic on these elliptic curves, so they leave the curves invariant. So that happens here. Then automatically the map extends to a globally defined map. It extends to a continuous map, and then by theorem on removable singularities is actually a holomorphic map, globally defined. And since the same holds for the inverse, the thing is actually a global diffeomorphism, complex analytic diffeomorphism. Diffeomorphism of S. This theorem is no longer true when you go to higher dimensional manifolds, which are fibered by elliptic curves. It's quite easy to find counterexamples to that, where the map is not everywhere defined, but in the place where it is not defined, it is really undetermined in the sense that by going to that locus where it is not defined from different directions, you get different limits for the image point. And that implies that you cannot even extend it to a continuous map. But in this situation with these dimensions, this is true. Yeah.
I just say you've written S equals this thing, but really S is the decentralization.
No, I didn't discuss that yet. I wrote it, but
Okay. But you're talking about S there and S.
Okay. So, since you brought it up, the claim is that if all base points are simple, or put in another way, if you have 8 base points, then they automatically are all simple, with 8 base points, then this surface defined in this way, you just look at this equation, but now in P1 cross P1 cross P1, in the 3-dimensional space. And as an equation for all the 3 variables, z, x, and y. And then that defines the surface, of course. And of course the obvious question is, why didn't you use this surface to separate the level sets? Because the projection to the first variable, let me call it pi1 here, that's the projection to this coordinate, that automatically makes the things disjoint. If you fix this one, then you do get your biquadratic curve. But since in this set, this biquadratic curve is the fiber of the projection onto the first vector, they become automatically disjoint. So why talking about this blow-up stuff? Yeah? So and if all the base points are simple, then this is actually a much simpler way of getting S. Completely explicit way, in the sense that if you believe that you can solve equations, then, and this is not so hard to solve this equation. For instance, you can solve it with respect to z. Yeah, then actually the surface which I got here has all the required properties, and therefore it is isomorphic. So then the S there is the same as the S here. Yeah. The catch, however, is that if and only if all base points are simple, this surface here is smooth. This is an algebraic surface in P1 cross P1 cross P1, and it need not be smooth. And you can very simple exercise to determine when do you have a non-smooth point, and it is precisely when the point x comma y is a multiple base point, then this surface is not smooth. So then you get a projective variety which is not smooth, and then you can say, oh, I don't mind. If you are a true algebraic geometer, you don't mind. But I am an analyst, and I do mind. And so what you do then is you desingularize the surface. And fortunately, there are general theorems about desingularization of surfaces that you can always do that and make it smooth. But in this case, you are even in a much better situation, namely the singularities are, in general, the singularities are, there are different words for the synonyms for what they are. They are simple, or called rational double point of surface. And there are some more terms which all are synonymous. So the singularities are of very simple nature. And it means that by doing ordinary blow-ups of points, you get a smooth surface. Yeah?
So this S
Yeah.
is isomorphic to the thing you've written down.
Oh, this.
Because it's equal
Let
to
me put in here a different letter, as defined by the pencil. Let me call it S pencil, which is directly defined in P1 cross P1 cross P1. If the base points are simple, then this S there is isomorphic to the S pencil. In general, you have the following situation. We have S going down to P1 cross P1, but also S pencil goes down to P1 cross P1, and you can put it in between. And there is a natural map from S to S pencil, and this is not smooth. If there are multiple base points, then this one is not smooth, but that one is smooth. And if you look at what this map is doing, then you see that over the singular points of S pencil, you get a curve. And in the complement, over the complement of the singular curves, this is an isomorphism. So this is a blow-up procedure to get that one.
In a simple case, does your argument on the blackboard on the right then imply that the second homology is at least 8-dimensional of this?
Yeah, that's actually what I wanted to start with after the break, to discuss the second
From that
homology.
point of view, that would be very surprising that you could sort of see right away that big.
Yeah. So from this blowing up 8 times, I get the following conclusion about the two-dimensional homology group of the surface S. I first have to start, of course, by identifying what this homology group is for P1 cross P1. And that's very easy. You have a horizontal axis, and this has a homology class, and I call that homology class of a horizontal axis, I call it L1. And you have a vertical axis, and it has a homology class which I call L2. And the point is that all horizontal axes are homotopic to each other and therefore homologous to each other, so they define the same homology class. So there's only one homology class in the H2 of P1 cross P1, which represents the horizontal axes. And then also, since intersection number is a homology invariant, you get that L1 intersects with another horizontal axis. They are disjoint. Different horizontal axes are disjoint. And so the self-intersection number of L1 with L1 is equal to 0. For the same reason, the self-intersection number of L2 with itself is equal to 0. And then the intersection number with L1 with L2 is of course 1. The picture shows this extremely clearly, but they have only one point of intersection, and the intersection is transversal, and so it's intersection number equal to 1. And so the statement is that this is equal to ZL1 plus direct sum ZL2 with this intersection form. With this intersection numbers are like that. Intersection of arbitrary homology classes just behaves bilinearly. So if you know what it's doing with the generators, you know what the intersection form is on this whole thing. So I prefer, because intersection theory plays an important role, I prefer to look at the H2 together with its intersection form. And you will agree with me that this has the matrix 0, 0, 1, 1, and it is a nice non-degenerate matrix of determinant equal to -1. And so for that reason, because the absolute value of the determinant is equal to 1, this lattice is by definition such a group, finitely generated commutative group, together with an intersection form, with a form on it, a z-valued bilinear form. And if the determinant of that is equal, absolute value is equal to 1, then it's called a unimodular lattice. So this is a unimodular lattice, but it is one of the simplest kinds. If you would start out with P2, that's another game, then the H2 is generated by only one element, namely the homology class of a projective line in the projective plane. And that has self-intersection equal to +1, because two projective lines intersect at one point. And so then the homology is even simpler. But I start out with P1 cross P1, so I start out with this situation. And then, every time you blow up, you get an exceptional curve, and blowing up further, you take what is called the total image, pre-image of that curve. And then you get homology classes upstairs in S. So I have E1 up to E8 are the homology classes appearing as the exceptional curves by the blowing up procedure. And in this way, this is equal to ZL1 plus ZL2, direct sum I equal to 1 to 8, Z times EI. And the intersection numbers are very simple-minded. EI intersected with L1 is equal to 0, because if you blow up at a point, then you can take a horizontal axis which does not go through the point, and upstairs you see that they are disjoint. So this is obvious. Then EI dot EJ is also equal to 0 if I is not equal to J, and EI intersected with EI is equal to -1, because all these P1s which appear, they have self-intersection number -1. And so this is the intersection structure on H2 of my surface.
Are you supposing the base points are distinct?
This happens if the base points are distinct. If they are not, the fact that you take total images instead of proper images makes that this remains true.
So this is for the full.
Yeah, you have to do a little bit of checking there, but another point is that if you have multiple base points, then these EIs which you get, these total images, they can be curves which are not irreducible, which are unions of a number of P1s. So then the EIs can look, the curves which they represent can be a little bit more complicated. But their homology classes do have this structure all the time. So one of the surprising things is that although you can start out with very different pencils of biquadratic curves and very different structures of base points, of multiplicities of base points, the manifold, the S which you get, always have isomorphic homology. And this statement has been inspired people to prove very strong statement, namely that the surfaces actually as real manifolds, real four-dimensional manifolds, are all diffeomorphic to each other. So as a manifold they are the same, but if you look at the complex structures they are very different. But as real manifolds they are actually diffeomorphic to each other, which is even much stronger than saying that they have the same homology group. But that's not of very much importance to what I wanted to say. So I want to present at least one theorem which is a consequence of the fact that this QRT map is now a globally defined map, and therefore it acts on homology. If you take a cycle, then its image under a diffeomorphism is a cycle again. So you get an action of the map on homology. Yeah? And I can compute the action on the homology under a condition. I can compute it, but I can compute it always, but the simplest statement is when I make some assumptions, simplifying assumption. In the other cases, the result is a bit more complicated, and I don't want to pester you with the general, with all the cases which you can write down. This one is already, looks already impressive enough, I think. The assumption is no member of the biquadratic tensor contains a horizontal or a vertical axis. That's the assumption. I already mentioned that this is, if you have a member which contains a horizontal axis, then on that horizontal axis the QRT map is not well defined. Nevertheless, if you pass to the surface S, the map there is well defined, even in that case. But then it turns out that the answer to what I'm going to write down is more complicated. So actually this condition is quite natural to separate that as a special case, nice special case. So if that happens, then I can tell you what this tau is doing on the homology classes. So I now use the same letter tau for the action on the H2, if you allow me. So then L1, the horizontal axis, goes to L1 plus 4L2 minus the sum of all the EI's. The L2 goes to 4L1 plus 9L2 minus the sum of all the EI's. And the EI goes to L1 plus 3L2 minus the sum of all the other EI's. So the sum of the EJ's, J not equal to I. This is the action on the whole homology, because if you know it on the generators, then you know what it is doing on the whole homology. And knowing this action, I have as a consequence, and I will explain this implication here. As a consequence, I get that the number for each positive integer k, the number of k periodic fibers, that means those fibers on which, if you look at the map on that fiber, if you take the k's iterate, it becomes the identity map on that fiber, that I call a k-periodic fiber. The number of k-periodic fibers is equal to k squared minus 1. Okay. So I present this theorem not so much, not really that you have to memorize it, but in order to give an example of how you can apply the fact that the map is nicely globally defined, because only that allows you to do this calculation in homology and have this kind of conclusions. Now let me explain a little bit more about how this implication is done. Because I want to make an observation about what happens at the last blow up over a given base point. So if the base point is simple, it's also the first blow up, and there's only one blow up over that base point. But if you have a multiple base point, you have to blow up several times, and I would want to look at the last blow up. What happens with the last blow up is the following picture, that in the surface which you have before you did the last blow up, all the curves had still a base point, one base point, but there all these tangents of the curves were distinct. You get this whole P1 of tangent lines of the curves at this stadium just before you did the last blow up. And now I do the last blow up, and then I get the following picture. You have the exceptional curve which appears at the blow up of that point, and then these curves, they become nicely disjoint. But what does this picture mean? This means that this exceptional curve which appears there actually is a global section of the vibration. It intersects each of the curve exactly once at the smooth point and transversely. Yeah? That's what happens. So, and this E is an embedded P1 in S, and it has self-intersection number equal to -1, and E is a global section, global holomorphic section. Algebraists would say regular or something like that. I don't know what algebraists would say here, but it's smooth. Yeah.
Just a very small question. In that last line, is L3 supposed to be L2? In the middle term.
This?
Last line, middle term.
This one?
Yeah.
This is 3 times L2. I only have L1 and L2. There's no other L. Yeah.
But which order you need to take when define how as the position of the horizontal and
First the horizontal, then the vertical one. If you do it the other way around, then you get the inverse of this action, and you can easily see that you get the same formulas but with L1 and L2 interchanged. Yeah, that you can see that right away. So this is a global holomorphic section. And now comes the point, yeah?
Yeah, I'm curious, if you look at S again in terms of P1 cross P1 cross P1, then probably it's possible to pin down the locus of this E very explicitly.
Yeah, sure. It is just you have this where it disappeared from the blackboard, but you have this surface lying in P1 cross P1 cross P1, and you can also look at the projection to P1 cross P1, and then you see that the pre-image of the base points, they are these exceptional curves E. So that projection is not a diffeomorphism, not at all.
Yeah.
This surface in P1 cross P1 cross P1 is not at all diffeomorphic to P1 cross P1.
So it's a much more concrete, nicer picture.
Yeah, it's very concrete. This is just a sort of an abstract way of describing what is going on. I could also have started with the concrete one and then observe that the projection to P1 cross P1 is not a diffeomorphism, and where it fails to be a diffeomorphism is precisely over the base points, where the pre-image of a base point is a P1. But then everybody in the audience who has a little bit acquaintance with algebraic geometry would shout at me that I'm blowing up the base points. So it's completely equivalent. Yeah? Only point is that if there are multiple base points, then this surface in P1 cross P1 cross P1 happens to have singularities, which you then have to resolve in order to get a smooth surface. I'm not very good in for instance, what is the H2 of a surface which has singularities? But when you resolve it, you get the same H2 as if there were no multiple base points. Does not, the topology doesn't change actually, not at all. Very uniform. But so we are in this situation that this E is a global section. Now I apply my automorphism tau S, my QRT map on the surface S. This QRT map leaves each of the curves invariant, and since it is an automorphism, a global diffeomorphism, it will map the smooth E to a smooth image curve, which everything is complex analytic diffeomorphism, so the image curve is also isomorphic to an embedded P1. So the image here will also be, and it is also a section, because the whole structure doesn't change actually. So I get another section. Now for the QRT map, you can easily verify actually that this image section is disjoint from the section I started out with. So not only you get another section, but it is even disjoint from it.
Because there are no fixed points.
There are no fixed points for the QRT map itself. Yeah, that's very nice. So now we have already two such sections. Also, because it's a global diffeomorphism, the self-intersection number of this thing with itself is also equal to -1. Everything remains sort of the same. Now I can start iterating the map. So I take tau S to some power k, and let me draw the picture for tau S to the power k, and let me draw the picture with some intersection points. I hope that there are colored, yeah, colored chalks. So this is tau S to some power k, image of E. And here I drew an intersection point. Then look at the fiber, the curve, through that intersection point. The map leaves the fiber invariant. It maps this section to that section, and therefore it leaves the intersection point fixed. However, because it is a translation on the curve, it leaves every point of the curve fixed. And therefore, the whole curve going through this intersection point will be fixed points under the case power. And so the statement which I now can make is that this number of k-periodic fibers in general, the general situation, is equal to, you take the S power, the case power of the map, you look at the image of the section, and then you take the intersection number of that with the section you started out with. And that is equal to the number of k-periodic points. Now it can of course happen, everybody will immediately make this remark, that you have a tendency of certain order here at such a point. Actually, it's very rare that it happens. I think I did not locate any example where that happens yet. So this is one of the open questions. Find interesting examples where you get nice tangencies there. That means that you have, in that case, I say that the k-periodic fiber has multiplicity equal to the intersection number of the two sections, how they intersect, the multiplicity of the intersection. So I count the intersections with multiplicity. Because if I do that, then this intersection number here is equal to, you just take if E is the homology class, small e is the homology class of capital E, homology class of capital E, then this is the same as you take the case power of the action of tau on the homology, let that act on the homology class, and take the intersection number with E. Yeah?
If you carried with you a free parameter, so you had a one parameter, then QRT could you just manufacture this thing?
Probably. I've not tried to do that yet. See, that's another, comes to another open question. If you have such an elliptic surface, it's defined by a pencil, but in the pencil you still have a lot of coefficients to play with. So you can let the whole pencil, and therefore also the surface, depends on these additional parameters. How does the picture change if you vary the parameters? I think that's a very interesting question. What kind of deformation of surfaces do you get with corresponding deformation of QRT maps, and therefore also corresponding deformation of these guys? How can you deform that? But for that, what you want to do, you need, for instance, to start out with two such intersections which are close to each other and then bring them towards each other. If you can show that you can do that freely, but I'm a bit careful not to make any statements here because I don't have any. And it is well known that the Italian geometers made a lot of such generosity statements, which some of them later out turned to be false. 90% of their statements were correct, but a few of them were not correct. You cannot always do perturbations as you like. So I'm a bit careful here not to make statements like that. So what you can do, for instance, is you can take, for your E, you just take the last one here, the E8, and then see if you iterate this map, this tau here, k times, apply it to E8, and then take the intersection number with E8, what happens? I will spare you the details of the linear algebra which is needed in order to compute it, but you can explicitly compute it. It's not actually too hard. And this is the answer, k squared minus 1. I like that answer, it's very, very simple. So what happens in general? In general, you, if this condition is not satisfied, then you have some members which are reducible curves. You have this horizontal axis or this vertical axis, or even both a horizontal axis and a vertical axis contained in your curve, so it has more irreducible components. Then also in S you will get a reducible curve. One of the curves will be reducible, and then the map can interchange the irreducible components. It acts on the set of irreducible components. And this action, this permutation action of the irreducible components, comes into all the answers. Now, since you have only finitely many such singular fibers, and each of them has only finitely many irreducible components, the finite power of this thing will leave all these components nicely fixed. And that means that the kind of calculus which I did here is becomes the same as if I started out with the original QRT map when this has come to at rest, if you understand what I mean, when there is no action anymore, when there's no permutation action anymore of the irreducible components. And so this then leads to the conclusion that in general the answer is as follows. You get a rational number q between 0 and 1 times q squared plus something which is periodic in k. Periodic in k. This is the general answer for the number of k periodic fibers.
Here, when you say k periodic, when k is not a prime number, are you counting as well the one which comes
Yeah,
from?
all multiples of k are also. Yeah. So I'm not talking about the minimal period. I'm just talking about that the k's power is the identity on that curve. It could be that, for instance, if k is equal to 100, it could be that already tau squared is equal to the identity, and such a curve will also be counted in the 100 periodic guys. You understand? That is needed to have that interpretation because that is needed if you use that geometric picture. Okay, there's one exception, of course, which I did not mention. The map could also be itself entirely periodic, meaning that for some power k, the k's power of tau is equal to the identity on the whole manifold. And then, of course, you have infinitely many things, and then all the curves are k periodic. That can also happen. And that's a special, very interesting question. When is the QRT map periodic? It happens once in a while. And Professor Tsuda, he's not here at the moment, but he is in this meeting. He found whole families of such guys. And one question which I would like to pose to him is, how on earth did he find them? Because he wrote them down without telling how he found them. So he apparently had a secret method of finding them. So this is one of the applications which I would like to give of the blowing up procedure, so that you get everywhere defined things. And I think that I should stop now, because I have now the opportunity to go on next week and treat other subjects. One of the things which I want to do next week is something which is also very natural. You have these elliptic curves, and everybody knows that an elliptic curve has a so-called Weierstrass normal form. So you have that the elliptic curve is isomorphic to a curve like this. In the plane. And one of the remarkable things about these pencils of biquadratic curves is that the whole family can be brought into Weierstrass normal form with the G2 and the G3, which are explicitly given polynomials in terms of the coefficients of the biquadratic polynomials I start out with. Completely explicit. And I was a bit surprised by that, because a priori I didn't expect that. I expect maybe rational expressions, but they are polynomial expressions. No denominators which make things... and that is a very helpful tool, because it is known that the curve is smooth if and only if the so-called discriminant, which is g2 to the power 3, g2 to the power 3 minus 27, g2 to the power 2, g3 to the power 2, the curve is singular if and only if this capital delta is equal to 0. And now it turns out that G2 and G3, in terms of the parameter z, which I have, are homogeneous of degree 4 and degree 6, respectively. So if you then look at the homogeneity degree here, you get 12 in both terms. So delta has homogeneity degree 12. So this is a polynomial of degree 12, and therefore it has 12 zeros, if you count them with multiplicities. And that is the reason why there are always 12 singular curves in the family when counted with multiplicities. But these kind of explicit formulas, they are useful for a number of things. And that's what I want to talk about next week.
Can I comment? Can you not also use these explicit formulas to give an alternative proof of your theorem? Because you can look at the x coordinate of the point that defines the shift on each fiber
Right.
And that will be a polynomial in Z.
Sure. Yeah.
And then you look at the division polynomials of
Yeah,
the curve,
sure.
which is polynomials of case.
You look at what happens in the denominator, and the polynomial which appears in the denominator equal to 0 corresponds to these intersection points. And you have to determine how many, what is the degree of that thing in the denominator. So if you look at the iterative construction of these denominators, the degree is equal to k squared minus 1.
Yeah,
But what can happen is that you have polynomial divided by polynomial, so you could have common factors. And if that happens, then you get fewer. And so you need something to determine when does that happen or not. And this theorem gives an answer to that. I do not know to do it in the purely algorithmic way which you describe. I do not know how to decide when there are cancellations or not. Right from the algorithm, I cannot see that.
I think this is something that one of my students just did in his thesis, actually. And, so he looked at the resultant of the numerator and denominator to see when they would both vanish. And they vanish precisely when a certain function vanishes, and that function is equivalent to Hahn's statement about having a horizontal and vertical axis. So classify the singularities that have that.
So you know he knows apparently how to do that via that algorithm. Very nice.
Yeah. I'll show you.
But is he also able to determine the degrees which you get after cancelling?
I don't think he went that far.
Because for that, I described this formula here, not in detail, but it is also completely explicit in terms of the combinatorics of how the map acts on the singular fibers. And, but I like to look at these things more geometrically, really. But of course, very beautiful if it also is confirmed by such algebraic.
Do you know which of the statements that the Italian geometers made are false?
No, I'm not an expert in that. I'm not just quoting what algebraic geometers say about the Italian school. The Italian school is clearly produced an enormous corpus of very beautiful mathematics, but in later times, I think in the time right before the Second World War, there came some doubts that maybe here and there the claims were not correct, and then the machinery was developed. Machinery like intersection theory was developed in order to decide these matters, and then it turned out that most of their statements were correct, but some were not correct. So especially those which were based on genericity arguments, which if you are too naive about that, in algebraic geometry, if the degrees are not high enough, then generic is not what you think.